All right. So having talked about the fundamental quantities, the what is it called, derived quantities as well too. And some common terms we need to put into place before ever going into um, solving dimensional analysis. You get it now? So here are just few of the questions, tough questions. So let's quickly go through them. The first question says the unit of moment. I get it now. The unit of moment of a couple is measured in. So that's the solution. The unit of moment of a couple is measured in. And like I said before, you ever try a question out. This is how to do it. Yeah, especially when you are on this aspect of physics. Before you ever try it out, understand the question now. Then know what you want to solve for. You get it now? This is a derived quantity. You get it now? Moment is a derived quantity. You get it now? Moment and a few others are also they are derived quantities. And I said derived quantities, they solely depend on the fundamental quantities. And having listed the 7 basic quantities we have. So this question is now telling us that the unit of moment, or it's telling us to look for the unit of moment. You get it now? The unit of moment. So this is how to do it. Solution, let's say moment. The first thing to do is you get the formula. You get the formula of moment. This is moment. Yeah, moment or torque. Yeah, and by formula it is given as, or it is given to be force times distance. You may be wondering that force times distance, yes, there's some cases like that too, in which two quantities they have the same formula. Think of stress and pressure. You can think of stress and pressure. Think of moment and work. Think of speed and velocity. Another case like that too. So meanwhile they are different. They may conform to the same formula, but they are different. You get it now? They are completely what? Different. Now this is moment of work. Moment is a vector quantity. You get it now? While work with the same formula is what? A scalar quantity. There's a reason for that. So let's continue. We are asked to look for the unit of moment of a couple. So it's quite easy. Now you have to check the question, you check the option. This is what we want to solve. We want to solve in respect to these options given. So it's easy. Force by its unit is given as force is measured in Newton. Force is measured in Newton. The distance, like you all know already, is what? In meters. So it's simple as saying moment is equal to what? Newton. How do I get it now? Moment is what? Newton times what? Meter. That's given as what? Newton meter. So, that solves this question, this particular question. The unit of moment of a couple is measured in. So the right answer is Newton meter. I hope you get it now. So the second question says, which of the following units is equivalent to kg ms raised to the power minus 1? Which of the following units? You have some options here. Option A says ms raised to the power 1, that is Newton per second. Option B says Newton meter second. Option C says Newton second. Option D says joule per second. We are not sure which should be the right answer. So we have to solve. We have to what? So I hope I can clean this. We have to solve. You get it now? So which of the following units is equivalent to? First thing, to bring it out, kg ms raised to the power minus 1. Now we have the options. Which of the following? This is how to do it. Kg, we have kg. This is a symbolic unit for mass. So we say mass. Then we have meter per second. That is velocity. Remember,
our mass is measured in kg. Okay, now velocity. The unit of velocity is what? Meter per second. Same as speed. You get it now? So the question is now simply asking that, okay, we've been given what? A derivation. Which of these options is what's called is similar to this particular stuff, to this particular dimension. So what do you do? Now this is what we have here, mass times velocity. Get it now? Now from our knowledge of momentum, we know that momentum, please note, momentum is different from moment. So momentum is given as what? Mass and what? Mass times velocity. That is momentum. Get it now? So we can as well say change in momentum. Let's say change in momentum is equal to what? Change in mass and velocity. Get it now? So change in momentum is as well change in what's called change in momentum is equal to what? Change in mass and velocity. So that would be mv. Get now mv minus what? mu. Change in momentum. That is it. So here we have. So remember that change in momentum is also equal to what? Force times time, or simply impulse. You know that impulse is given as F times t. Change in momentum as well is given as well. Force times time. You get it now? So, let me bring this one. You get it now? So, change in momentum is given as force times time. So, it's as simple as saying, what's our force measured in? Force is measured in Newton. You get it now? Force is measured in what? Newton. And time in seconds. You get it now? So, that's why option C is correct here. Newton second. So Newton second is what? Is similar to kilogram per meter second. So this is it. Then the next question. Let me clean this. The next question. I hope you guys are getting that. So I hope I can clean this as well too. I can clean this. So the next question is at what now this is a common case in exam. At what respective value of x, y, and z would the unit of force, the Newton, be dimensionally equivalent to m raised to power x, l raised to power y, and t raised to power z or z? So it's very easy. You get it now? It's very easy. Now look at what they are talking about. They said at what respective value. Now they give us a derived unit here, which is force. You get it now? They gave us the formula to follow. So by dimension, force is what? mLt raised to power minus 2 by dimension. You get it now? Now the question is at what respective value of x, y, and z? So what we are going to do is that we want to compare this with this. So it's as simple as saying force is what? Then you bring it in m raised to power x, l raised to power what? Y, z raised to power c raised to power z. How do I get it now? So then you want to compare. You bring this in mn c raised to power minus 2. You want to compare the two. mx l raised to power y c raised to power z. So if you check this one now, you get it now. We have an invisible 1 here. So let's say n raised to power 1 is still the same thing. So even if you have 1000 raised to power 1, it's still 1000. M raised to power 1 is still the same as 1. So there is an invisible 1 here. There's equally an invisible 1 here. So we want to compare like this now. So if this is m and we have m here, you have to compare, you want to compare their powers. Again, you are trying to compare their powers. So in this case now, it is simple as in x is equal to what? 1. It is safe to say that x is equal to 1 because it is obvious that their powers are what? What's called? You are trying to compare their powers. So if m is carrying x, then m1 is what? So you consider these two, since they are similar, you consider these two and you equate their powers. So x is equal to what? 1 automatically. Then for our n, our y is equal to what? Y is equal to what? 1 also. You get it now? So now back to t. You get it now? You know they are similar as well too. So our t is also what? Sorry, our z or z is equal to what? Minus 2. So you can see that is now. So now back to the question. At what respective value of x, y, and z would the unit of force, the newton, be dimensionally equivalent to this? So we have 1, comma, 1, comma, minus 2. Get it now? 1, comma, 1, minus 2. And that's what? 1, comma, 1, minus 2. So option B is correct. So that'll be a little more. Option B is correct. Okay, so in any in any case you have something like this, you look, the first thing to do is you look for the dimension of the unit given, be it pressure, be it stress, be it work, anything. You bring in their unit, you bring in the unit, then you compare with what they give to you. So here's another question. Let's quickly check through. So how I can claim this? So here's another question. Now please pay attention. Alright. The values of x, y, and z respectively in the expression, look at it, here's the expression. So you see, you bring it out. M x L y c raised power z. This is the expression given in the question. For the universal gravitational constant, you can see the universal gravitational constant. Now, from our knowledge of the universal gravitational constant, or from our knowledge of Newton's law of universal gravitational constant, this thing, Newton's law of gravity. This is what you do. You bring in the formula, the relation. So this is it given as what? It says then r squared. You get it now? Radius. So here is another unit in which you can use meter for. Again, you can use meter for this unit, radius. So now, if you express this, you have something like, to remove this proportionality sign, you bring in a constant. Again, you bring in a constant. So the constant used here is G. This is the universal gravitational constant they are talking about. And capital N over r squared. Get it now. But in this case now, since radius is also what? As a result of distance, it is safe to say F is equal to what? G M capital M small m over d squared. Get it now. You can use d squared following the law. Get it now. This is the expression of the law. F is equal to GM over d squared. Now the question says the values of x, y, and z respectively in the expression is for the universal gravitational constant. This is what we are concerned about. G. So what do we do? In this case, you cross multiply over 1. Here and you cross multiply. So when you cross multiply, you have something like FD squared is equal to what? G M M. Get it now? Then you make G the subject of the formula because that's what we want to work on. So you have something like G is equal to what? F d squared over capital M small m. Now this is the expression. This is what you need to what? Compare with this. This is what you want to compare with this. G is equal to f d squared over m capital M small m according to the law. So now you have to look for the dimension of this one before ever comparing with this, because that's how to do it. Anyway, you see something like this, you make sure you look for the dimension of the units given, then you compare with them, just compare their powers. Then you compare their powers. So this is how to do it. So G is equal to what's the unit of force? This is force. This is what's called distance. So what's the unit of force? By dimension, that force is given as what? MLT raised by minus 2. Get it now? MLT raised by minus 2. So you can even bracket this one. Then the unit of distance. Get it now? The unit of distance, remember, is what? L. You can use L. So let's say you can use L, you can say dot L square, since this is D square. You get it now? Over, you have M, or no, let's do it this way. Let's do it this way. Let's say G is equal to, we have force. By formula, force is given as what? By formula, force is given as what? Mass times acceleration. By formula, force is given as mass times acceleration. This will be much more easier. Then times what? So our D, you can use L square, you get it, and then over capital M, small m. You get it now? So please follow and pay attention here. You get it now? So this is M, this is M. What do you do in this case? You cancel out. Then you are left with what? A. In fact, you can still leave this one as your D. You get it now? For better understanding, you can say A D squared over what? Capital M. So this is your new expression for what? For G. A D squared over M. Remember, I want to compare. So this is A D squared over M. So what is the dimension of acceleration? This is acceleration. What is the dimension of acceleration? Very simple. Acceleration is given as what? LT. This one minus 2. You get an LT raised power minus 2 times distance. Now you can now say, you can now change your distance to L. L squared. You get it now? Over. This is mass. You get it now? Over M. Are you getting me now? So now, this is L and this is L, right? They are two similar variables. Now you have to add their power. Get it now? Following the law of indices. That will give us what? L raised power 1 times L raised power 2. According to the law of indices, will give us L raised power 1 plus 2. And that is L raised power what? 3. Get it now? That is L raised power what? 3. Then times T raised power what? Minus 2. It is obvious. Minus 2. Then times, remember I said, anywhere you have over m, you can as well express as what? 1 over m. Get now, as 1 over m. Let me do it this way, so you don't get confused. So it's equal to, you have it as n raised power 3 times what? T raised power 2 times what? According to the law of indices. So anyway you have a case like this, you get it now. You can now say your m returns to what? I've once expressed this one. Minus 1. You get it now? Minus 1. So this is what you will have for the expression. Then you can now arrange in conformation with what you have here. You get it now? So let's arrange. So it's going to be what? M raised power minus 1. M raised power minus 1. Then N raised power 3. C raised power minus 2. You get it now? And this is your dimension. This is the dimension for what? For gravitational constant. Now, what do you do in this case? How can I play this? So the next thing to do in this case is you now want to compare. That's how to do it. You compare their powers. This is an expression, this is another expression. So you bring this in and say G is what? M raised power what? X. N raised power Y. T raised power what? Z. Then you now bring this in for G, your dimension. That will be what? M raised power what? Minus 1. C raised power, okay. L raised power 3. C raised power what? Minus 2. So Mx, My, T, Z. How be I following? So now you want to compare their powers. That's how to do it. The values of x, y, and z respectively in the expression for universal gravitational constants are. You get it now. So what do you do now? You have m, you have l, you have t. You have m, you have l, you have t. But their powers are different. So automatically we are saying these bases are equal. You get it now. So you now have to compare their powers. So it is safe to say x here is equal to what? Or you can even bring this one further by saying m raised power minus 1 is equal to what? M raised power x. That's if you want to do it mathematically. Since these two are different, you can cancel them out. Your x turns to what? Minus 1. You get it now? So x is automatically minus 1. So for you not to go through this stress, you can just say your x is equal to -1, y is equal to 3. But if you want to express yourself, L is equal to L raised to power 3 is equal to what? L raised to power y. These ways are equal. You get it now, but the powers are not. So you can cancel them out. Y is equal to what? 3. So x is -1, y is equal to 3. Then t raised to power z is equal to what? Or t raised to power -2 is equal to t raised to power this. So you can cancel them out. Then z is equal to -2. So your x, y, and z now. X, y, and z. What's our x? We have -1. What's our y? What's our y? Our y here is what? 3. Then what is our z here? What's our z? We have -2. You get it now? -1, 3, -2. We have -1, 3, -2. And that is option B. You get it now? So this is how to do it. So in any in any case, in any or if there is any question bringing out something like this, what you need to do is get the dimension of the unit. You get it now? Get the dimension of the unit, yes, of the derived unit in most cases. Then compare with the given dimension, and that's how to do it. You compare their powers. Alright, so let me just add one. Let me add one dimension to it. Then you can solve more. Go to your past questions and solve more.